We're going to look at exponential functions. Okay, hear me out. We're not going to do the graphing. I'm not going to make you graph it, but I want to show you the graphs because there's a big difference between an exponential function and a linear function. Linear functions are steady. All right, you can think of it like a set of stairs. You go up and over the same exact amount every single step that you take. All right, and so a linear function is very steady. You're not going to see a jump. It's going to just rise exactly the same the whole time. All right. Exponential does not do that. So you'll hear someone say it grew exponentially. What they're actually saying, if they don't mean it mathematically, is it's growing really quickly. You'll notice on an exponential function, it starts here. And while it looks like it's doing this track, it shoots up, right? And so that's what happens with exponential growth. Or exponential decay, which we're going to get into in the next section. It will drop that quickly as well. All right. So you see things like population growth is actually exponential, not linear. We don't grow by the same number of people every year. We grow in an exponential format because you have people having children and then you have those layers then having children. And so we have this exponential growth that happens. Exponential decay, you see that with depreciation. Things do not depreciate in a steady downward slope. They depreciate quickly. So what will happen is you'll see a really strict depreciation and then it may level off, like with a car. You buy a car, it's going to depreciate more in the first couple of years, then later down the road it'll kind of even out, right? And so those are the types of exponential. And so you'll see all of these graphs, whether it is the standard graph, which would be a growth, or whether it goes down, which would be decay, you will see these exponential graphs, and they look different than a slope, a linear graph. Linear graphs are going to be steady lines. These are going to be shooting up or shooting down, okay? The most famous of your exponential growths that you will see is your compound interest, which is really all we're going to do today is compound interest. The basic formula for compound interest is this formula right here. A equals P times 1 plus R to the X. However, that is assuming that you are compounding once a year. All right. So the more common one is the one that you need to be familiar with. And you want to write this down because I don't know that they actually wrote it out in the way that I'm about to give it to you. So your A represents your account balance that you're going to end up with. Your P, that stands for principal. That's the amount that you actually invest, or if you're borrowing money, that's the initial amount of the money that you're borrowing. You have your 1 plus. Assuming that it compounds annually, this is just your R. But some things can compound differently, all right? Investment accounts, they can compound quarterly. They can compound annually. They can compound monthly. If you look at something like a credit cards compound every month, okay? So every month they add interest to that, and then the next month they charge you the principal and the interest times the interest. That's compounding. This formula is now going to be your rate, that's your annual rate, over the number of times it compounds in 1 year. That's what your N stands for. The number of times it compounds in 1 year. And then your exponent is not just going to be an X. It is going to be the number of times it compounds in a year times the number of years that you are compounding it. Okay? So, while they didn't really spell it out here, this little X right here, N represents your number of time it compounds, which tells you over there, per year, and T represents the number of years, okay? And so this is the formula you're going to look at when you do compound interest, all right? So let's look at a couple of examples, and then we're going to do a worksheet. Look at example 4. This is on page 346. Mr. Menzik invests $10,000 in a CD, earning 3% interest compounded daily. Write an exponential function modeling the value of his investment after T years. Then use the function to find the value of the account in 25 years when he retires. So $10,000 is my initial investment. That is my P, my input. Interest is 3%. You always want to write your interest as a decimal. So I'm going to write my interest as 0.03. It compounds daily. If it compounds daily in a standard year, how many times in a year is it going to compound? 365. And then 25 years, that is my T. So I'm going to say the account balance is going to be my initial amount, $10,000, times 1 plus my rate. What is my rate? 0.03 over the number of times it compounds in a year. That would be 365. And I am going to raise that to the 365 times the number of years, all right? In this case, 25, all right? In your calculator, if you have a TI-85, like that keeps it for you, you can literally put all of this into your calculator at one time. You can say 10,000 times and have parentheses 1 plus 0.03 divided by 365, close parentheses, use that little caret top button that looks like that. You have to do parentheses here or it will raise it to the 365 and then it will assume your answer is multiplied. So parentheses here, 365 times your 25, close parentheses, and then you can hit enter and you will get the answer. If you have a smaller calculator, one that doesn't give you all the options to do parentheses, then you may have to do the individual pieces. So you may have to do this piece, you may have to do this piece, and then you may have to say whatever this is, answer, and take it to the answer here, those, and then multiply that by the 10,000. So pay attention to what kind of calculator you have. I want you to all try it in the calculator that you have because you should get 21,169.35. The first one we're going to set up, if we're looking for the final amount of what it will be at after 40 years, we would say, take that $10,000. You're going to multiply it by 1 plus. The first one is compounded annually. So really when it's compounded annually, you just have to add, it's going to be your rate in decimal form divided by 1, which is just like that, raised to just the number of years times annually. It's compounding once a year. And so this is the first setup to get the 128,910. So this is how the 3 should have been set up. All right, pay attention to your calculator. All right, your calculator will always do order of operations. So in your calculator, you can put 10,000 times, open parentheses, 1 plus this division, because it will do the division first, which is what it needs to do. Close parentheses, Depending on your calculator, you may have to do a parentheses here. Some calculators pop it up into the exponent and they don't come out of the exponent till you physically push the arrow to tell it to. Other ones will assume that the first number is the exponent and then that multiplication is by the answer, okay? So if you may want to pay attention here and put parentheses 40 times 365, close parentheses when you put it in your calculator, depending on what type of calculator you have. So we specifically talked about investment, which is an exponential growth function. You'll notice that these functions are always going to be in the form of y equals some constant. When we looked at your investment, your initial investment was that a part. And then you have something taken to a power. And for an investment, it was 1 plus your rate taken to the power, or 1 plus your rate over how many times it compounded taken to a power. But they will always be in this y equals ab to the x form. And so for this one, they've given us 2 points that fall on this particular exponential function, and they want us to find the function itself. So what we're going to do is we're going to take this form, and we're going to plug in what we know. We know our x, and we know our y, and we know 2 of them, actually. So we're going to set up 2 of these. For the first one, my y is 12. That equals ab to the x, which is 2. And then for the second one, my y is 96, which equals a b to the x, which is 5. So from this, we can actually solve. The way we're going to solve it is we are going to get them equal to the same constant, or the same variable. And then once they're equal to the same variable, we can set them equal to each other. So I am going to look at this left one here, and I'm going to divide both sides by b squared. So I will get that a equals 12 over b squared. And then I'm going to do the same thing over here, divide by b to the 5th, and I will get a equals 96 over b to the 5th. So now I have 2 equations that are equal to the same thing, which means I can set this part equal to each other. Substitution. If 2 things are equal to the same, you can substitute in. So I'm going to say 12 over b squared equals 96 over b to the 5th. All right? And I'm going to get all my b's to one side. So I am going to multiply both sides by this b to the 5th. All right, over here it will cancel. Over here, 2 of them will cancel. So these 2 will cancel with these 5. And I'll end up with 12b cubed equals 96. All right? Then I can solve this. What do I do to solve it? Divide both sides by what? By 12, right? Well, let's get b by itself, all right? So what is 96 divided by 12? Yeah, it's 8. How do I get rid of b cubed? What do I do to both sides? Cubed root of both sides. What is the cubed root of 8? 2. My b equals 2, all right? So I'm not quite done here. I need to actually solve for a. I can go back to either one of these and solve for a. I'm going to do the one that has the smaller of the 2. So if b equals 2, I can say, well, 12 equals a times 2 squared, right? 2 squared is just 4. Divide both sides by 4. A is what? 3. So now I have this right here. And in order to solve it, I really have all the numbers filled in except for x and y. So I'm going to take my a and my b that I solved for, and I'm going to rewrite this guy. I'm going to say y equals a, that's 3, times b to the x, 2 to the x. And this will be the formula for all of my numbers that are on that equation, on that function. All right? So it's just like when you had a y equals mx plus b, and you had to solve for the slope, and you had to solve for the b, the y-intercept, and then you had to go back and plug it in, right, and give me the y equals mx plus b form. This is my standard exponential form, y equals ab to the x. So one way you can tell if this is growing or if it is shrinking is based off of the rate, all right? We can look at the rate. So if you look over here, the form is y equals ab to the x, or b can be written as 1 plus my rate. Think about when we did investment accounts. When we did investment accounts, we took our initial principal and we said 1 plus my rate to the number of years that I did it. All right. So B actually represents 1 plus my rate. So if I am trying to figure out if this is growing or shrinking, then I can look at my rate and I can look at the B. The B is called the growth factor. All right. So if we look at these, we can say, all right, I have this formula, y equals 10 times 1 plus 0.5 to the x power. If I look here, my rate is 0.5. So my rate is greater than 0, greater than 0. If my rate is greater than 0, that's going to grow. That's like having an investment account with a 50% rate. That's definitely going to grow. All right, so this is going to represent growth. All right. What about this one? Well, if I look at my rate, 1 plus technically a negative 0.25, this is actually going to decay. So if I put something in this account, it's going to shrink, whatever it is. Usually you look at it for something that's decreasing, like a depreciation. All right. What if they've already combined it? So let's look at this one right here. Well, the only way to get to 1/2, if I start at 1 plus a positive or a negative is going to get me to 1/2. How do I go from 1 to 1/2 with addition? I have to add what? This has to be negative here, doesn't it? Which means this guy is going to decay. It's going to be getting smaller, right? This one's already combined as well. It's a 3 though. I start at 1. Do I add a positive or a negative to get to 3? This has to be positive to get to 3, which means this guy is a growth. So even if it's already put together, you can tell based on whether that is smaller than 1 or bigger than 1, if it is going to be a growth or decay. Beginning with a population of approximately 2 million people, Nevada was the fastest growing state from 2000 to 2010, with an average annual increase of 3.2%. Write an exponential function modeling the population growth in millions of people. So instead of writing 2 million, we're just going to write 2. Use the function to determine the 2010 population growth to the nearest 100,000. Determine the average annual percent increase in population during the 90s if the 1990 population was 1.2 million. All right. So the first thing we're going to do is we're going to set up a function of growth. We're going to do this just like we did our investment. This is an annual rate of increase. So my population, and we'll just name it, usually they'll do something that represents it. Population based on time. We're going to start at 2 million. Remember, it says in millions, so we're going to say 2. 1 plus, what was my rate? Well, my rate was 3.2%. How do I write that as a decimal?
0.032.
Yes, so 0.032. All right. And we're going to raise that to time. And so we can simplify this. We can say 2, and that's 1.032 to time. So that's what my first one would look like. That is the exponential function that models the growth. Then they want to determine what it looked like in 2010. So this is starting in 2000. They started with 2 million. So in 2010, that is 10 years later. So I'm just going to take this guy and plug in a 10. I'm going to say, well, my population after 10 years then is going to be 2 times 1.032 to the 10th power. That is approximately, by the way, 2.7 million. All right. The average annual. So they want to know what was the average from 1990 to 2000. So if I know in 2000 I had 2 million, that's actually what my account would be worth. And I started at 1.2 million there. They want to know what my rate was in those 10 years. All right, in those 10 years. Now you can do this. I'm going to show you how to do this. We're actually going to do this a different way later on. We're going to divide by that 1.2. How do I get that 10th power out of there? What do I do? Yeah, well, it's the square root. So I'm going to do the root, but instead of square, I'm going to do the 10th root. All right. And then I've gotten rid of it over here. So I have the 10th root of 2 over 1.2 equals 1 plus r. And I'm just going to subtract that 1. And we will do this in our calculators too, obviously. That's going to be my r. The growth rate then was about 5.2% if you were to do that. About 5.2%. So population growth slowed down in the next 10 years because it was only 3.2 after that. So when you look at growth, they tell you it increases. You automatically know we're increasing. We're going to add that to 100. I'm going to add that to 1, not subtract that from 1. It is a growth. When they said 2010 and we started in 2000, that gave me my number of years. And so this is just like if I were to invest money, compounded annually for 10 years at a rate of 3.2%. So you'll notice this pattern is the same for exponential growth. Even though it says population, you can use the same concept as you would when you were investing your money. Conceptually, it's the same. After Nevada's silver rush, its population fell from 60,000 in 1880 to 47,000 in 1890. Use an exponential decay. All right, exponential decay. So here's what we do. Exponential decay to determine the average annual percentage decrease in population. They have given us where it ended. So think of that as your account balance. That's 47,000. It started at 60,000. That's your initial amount. That's your starting amount. We do not know the rate. They are actually asking that annual percentage decrease, all right? Annual percentage decrease. So my rate's actually going to be a negative number when it's all said and done, all right? We do know how many years. It went from 1880 to 1890. So what's my time there? How many years is that?
10 years.
10 years. All right. So how do I solve for my variable? What do I need to do first? Divide by that 60,000. So I'm going to divide both sides by that 60,000. You can automatically get rid of those zeros, by the way. All right. So over here I have 47 over 60. Here I have 1 plus r to the 10th. All right. Now I need to do my 10th root, but in my calculator that's a little bit of a pain. So what's another way to write 10th root? I can raise it to what power? What can I raise both sides to a power?
0.1.
Yeah, 0.1. 0.1 or 1/10, the reciprocal, right? So I can raise both sides to 1/10. So in your calculators, this is what I want you to do. I want you to say 47 divided by 60, that's in parentheses, and I want you to raise that to the 0.1 power. The 0.1 power. Approximately 0.976. Okay, that equals 1 plus r. I still haven't solved for r. What do I need to do?
Subtract that.
Subtract 1. What happens when you subtract 1? What do you get for r? Negative 0.024. If I put that into percentage, my percentage rate is negative 2.4%. Does that make sense? Yes. What did they tell me about the population? It fell, right? When you see that word in a word problem, your rate should be negative. If it isn't, you did something wrong, okay? Your rate should be negative there. Negative 0.024 is going to cause the population to decrease, all right? If we wanted to then estimate this for 1900, we would just take this and take it to the 20. We would say, well, 60,000, 1 plus my negative 0.024, raised to from 1880 to 1900, that's 20 years. 20 years. Or you could start at the 47,000 and go 10 years if you wanted to. All right, they both work. Questions on population decrease. If you want to just consider the birth rate, 2.55 million is your starting, 1 plus your birth rate, okay? For death rate, it's a little bit different. You can't just combine those two because the death rate also includes the births. So your birth rate, this is now your initial. So you can't just start at 2.55 million. You have to consider that you have births in there as well. So you can take this as your initial. This whole thing is now your initial, and your rate, that is being multiplied by your death rate. You'll notice that I put a minus here. It's technically 1 plus a negative because death rate means population is decreasing. So that's where they got this 0.994. They took 1 minus 0.006. So this became my initial, and this was my new rate. In 6 years, you just had to plug a 6 in for both of these, and you should have gotten 2.65 million. And then we will do an easier way to solve this than doing roots, but we're about to walk into logarithms in the next section. Radioactive decay. So with radioactive decay, you have what's called a half-life. The half-life is how much something decays in a matter of time. So your base here on your half-life functions is 1/2. Basically what you're doing is you're taking the amount that you start with and you're cutting it in half. All right? You're cutting it in half every so many years. So it'll say if it cuts in half in 3,000 years, okay, then it'll take 3,000 years for whatever you started with to cut in half. If you started with 10 grams, in 3,000 years, you're going to have 5, okay? That's what half-life means. And so a lot of carbon dating is based off of this. There are some problems with some carbon dating, all right? Other elements that can affect it. But these are the basics, all right? So they've given us the half-life of carbon-14. The half-life of carbon-14 is about 5,730 years. That is a long time, okay? Which means if you start with any number of grams of carbon-14, it's going to take 5,730 years for that amount to be cut in half, all right? And so the formula here is your initial amount. So that A is always your initial amount. Your B here for a half-life is going to be 1/2. And then you put T, the length of time that it takes, that you have, passed, however many years, divided by that element's half-life, whatever that is. And each element has a different one. So you have to know the half-life of the element you're dealing with. In this case, carbon-14. 5,730 then would be our H. The piece of wood believed to be 4,000 years old now contains 19 grams of C14. Predict the original amount. Predict the amount to the nearest tenth of a gram in the wood 100 years from now. All right, so we actually know how much we have right now. So based on this, how much C14 do we have right now? Based on this problem, how much do we have? We have 19 grams. We are finding the original amount. So which of those do we not know? Which of these do we not know? A, we don't know A. We always use 1/2. All right, the piece of wood is believed to be 4,000 years old. Which variable is that? T. And what is my half-life then? What is the H?
5,730.
All right, you can do this in your calculator. How do I solve for A? What do I divide by? I divide by this whole thing right here. So you need to try this in your calculator and make sure you can do it in your calculator. My A then is going to be 19 divided by, and you are going to do this whole thing, 1/2. So in your calculator, obviously, what is 1/2? The easiest way to do that is 0.5 raised to the, you do need to do the 4,000 divided by 5,730 in parentheses there, all right? So in your calculator, it is going to do order of operations, so you have to force it to do what you want it to do, meaning force it to do this division before it does that 4,000 exponent, okay? you should get, by the way, approximately 30.8 grams. So make sure that you can put that into a calculator and get 30.8 so that you have done your calculator entry correctly. 30.8. All right, 30.8. Now here's the thing. Pay attention. There are two ways to do this next one. My initial amount was 30.8 if I'm talking 4,000 years ago. All right, 4,000 years ago. If you are predicting from this point forward, you could use your initial amount of 30.8 and do 4,000 plus the 100 years. But what could you also do if you're doing from this point forward? What could your initial amount be? What you have right now, okay? So in your calculators, when you're setting this guy up and you want to predict what you're going to have 100 years from now, you don't necessarily start here. If you start there, your time is going to be 4,000 plus 100 because that's what you had 4,000 years ago, all right? If you want to just do 100, you need to start where you are right now. Your initial needs to be that 19. And then you say that 1/2 to the 100 over your half-life, okay? Again, you can do that in your calculator, but pay attention to your division there. Your division has to all be in your exponent position, all right? And so 100 years from now, you will have approximately 18.8 grams. You can see that it slows down, right? Because initially, if it cuts in half after that many years, you have a large thing in half. Think about when you're taking a piece of paper and you're folding it in half. The first fold takes a lot away from that paper, right? But the smaller you have, the smaller your halves are. Does that make sense? So 100 years from now, you're only going to have 18.8. You've only lost 0.2 grams, right? Because you've only done 100 of your 5,730-year half-life, okay? So your half-lives are exponential because they are slowing down. They're not as big of a jump as that first one was. All right, your half-lives.